Good afternoon, everybody. Sam already mentioned that this project was actually developed by Antonio Di Nardo, who's one of our customers, lead CFD engineer at ENEA in Rome. And the application that we're going to talk about today is this one there. Basically, let's first of all have a quick look at the agenda. So what are we going to say? I will need to obviously say a couple of words about ENEA, what they're doing, about OMIQ, which is us. Then we'll give you an introduction to the project. We'll look at the dual fluidized bed description, and then we'll talk about Barracuda and how we set up the model. And then we'll come to some brief validation of the chemistry scheme that was used in the simulation. And then we'll come to the results, which actually is the most important part of the whole presentation, in fact. And then obviously we'll come to the conclusions. ENEA, that's spelled actually ENEA, but it's in Italian we say ENEA, right? Used to be originally the National Institute for Research into Atomic Energy, but then over the years it's actually changed and is expanded the focus of its research project into all sorts of energy transition and CO2 capture, all that anything which has got to do basically with renewable energies and environmental aspect of the energy sector. And OMIQ is the Barracuda Virtual Reactor distributor for Italy. We are a relatively small software engineering company focused on CFD simulation, and we normally focus and concentrate on vertical solutions, and fluidized beds is one of these vertical solutions that we market and support in Italy. The story of this project actually starts a few years back because in the ENEA Center just outside Rome, it was set up a pilot plant which is called ZECOMIX. And the idea of this plant was to actually investigate a few different strategies to generate either H2 or steam, and possibly with obtaining zero carbon emission. So there have been a number of projects with that. Actually, if you go back in literature, you will see some other applications where this ZECOMIX plant has been validated with Barracuda. In this particular case, the setup was a dual fluidized bed for continuous processing with a reformer, a calciner for solvent regeneration. So to be able to produce H2 and at the same time capture CO2 using bifunctional particles. So basically particles which are both catalyst and solvent. The plant and the setup can actually be schematized as in the picture you see there. We have a bubbling reformer which works at around 650 degrees Celsius, I should mention, and a partially bubbling calciner reactor, which is on the left side, which works at a higher temperature. It's actually partially bubbling because it was calculated that it was necessary to provide enough time to the particles to be actually regenerated. Then at the top, we have a cyclone for separation of CO2 gas and particles, a loop seal that would somehow avoid that CO2 to go into the reformer. And at the bottom, we have an inclined calciner inlet, which is actually a pipe which brings particles from the reformer to the calciner. There is a very rudimental particle flux control system, which is basically an orifice that can be regulated to, in case the flux of particles is too high, to keep it balanced, basically, to keep the circulation of the particles balanced. I should mention that both fluidized beds need to be fully functional. They need to be they need some thermal input, which is mentioned here. We modeled the whole system in one single setup. The overall mesh was 1.1 million cells with some refinement to be able to capture all the geometry features. As for the drag models, there was actually a decision by Antonio, by our colleague at ENEA, to use the EMS EMMS drag model, because they had validated in the past and they found that for these heterogeneous structures that was actually working well. Circulating in the system, there is only one particle species, which is actually these bifunctional particles, which are made of 60% of CaO when they're new, of course, 10% of nickel as catalyst, and 30% of inert support. Particles of around 500 microns when they're new. In terms of inlet conditions, the fluidization gas mixture at the reformer, actually there's a mistype there, it's steam and methane with a steam over methane ratio of 3 and a superficial velocity of 2.5 times the UMF. Calciner is actually fluidized only by CO2, and the loop seal gets an inlet gas, gets steam for the inlet gas. Some more detailed information are actually in the table on the side, or you can find them on the paper, which is actually being published last year. In terms of chemistry, the steam methane reforming was actually, the scheme was actually taken from literature, as it's mentioned here by Numaguchi and Kikuchi. The CO2 sorption actually was developed inside at ENEA. Stefano Stendardo is a good friend and has been researching this type of reactions over the year. The sorption rate is actually his own model. And there are a few papers about that. I mean, if you want, I can provide references about that. And as for the calcination reaction, again, it was taken from literature. It's a scheme that was found and designed by Fang and others, and it was actually, there were some data, TGA experimental data fits that would help fitting the parameters for this specific case. Validation is I mean, has been carried out on a lab scale reactor, a very small reactor actually. Again at ENEA, there were it was some experimental was carried out. Experiments were carried out with having, in this case, two different type of particles, so calcine dolomite for the sorption and nickel based catalysts. And you can, as you can see here, that actually the validation of the chemistry scheme, which was actually set up in Barracuda, was quite good, both in terms of CH4 conversion and CO2 and H2 mole fractions. So So being confident about the chemistry scheme, we set up. We started looking at running this model. The whole model would actually run. We estimated it would run in weeks before it could actually reach some steady state behavior. I should mention that at the time that this case was actually run, ENEA was undergoing an upgrade of their hardware. So maybe today it would be easier to get results quicker than what was it than what we was planned at the time. So what we did, we thought to reduce the initial transient, and the idea was actually to initialize the particles in the reformer using a reformer-only model, and which would be smaller, obviously, and get it to run. And so basically, the particles in the reformer are not initialized as completely clean and regenerated, but they're already been somehow partially used, let's say, right? And what you see here on the side is the CAO conversion rate that was obtained from the reformer-only simulation, and this was actually the composition that we used to start off the whole model. Let's have a look at the results. The project actually was designed, because this is an ongoing project which is still actually running at the experimental level. The whole setup and the idea of the project was, first of all, to check that the two fluidized beds would be sealed or insulated in terms of gas circulation. So we wanted to avoid and make sure that there would be no CO2 crossing into the reformer and no H2 going into the calciner, for obvious reason, to get the best possible efficiency and quality of the H2 production. So the first thing we looked at was is the time average pressure profile in the system. And if we concentrate on the two communication paths between the two fluidized beds, we can see in the inclined pipe at the bottom that the pressure, which is the pressure in KL01, which is actually the bottom of the calciner, is probably it's actually the point with the higher pressure in the whole system. And definitely it's much higher pressure than the ref O2 point where particles are picked and pulled into the inclined tube. That means that we have a negative pressure gradient in the pipe, and that should prevent H2 and steam to actually go in that direction. The second thing that we did, the second check that we can do in this profile is actually on the top part of the system, where we can see that the call-out pressure is quite low compared to the LS, to the 2 points that we put in the monitoring points that we put at the bottom of the loop side, and that again makes it a negative gradient for CO2, and that should prevent, let's say, circulation of flow, a CO2 flow going into the reformer. But just to make sure, if we can look at the solid distribution across the system, And in fact, we can see that in terms of particle speed, first of all, we could notice that in the inclined pipe here at the bottom, there's basically particles have almost no velocity at all. They're just moving out of gravity, just rolling into the calciner without being actually transported by any flux. And in fact, it's, you can also notice that the particle volume fraction is fully packed. On the other hand, you can see, okay, that the riser here generates quite a good speed, but also that the mass fraction of CaCO3, so the conversion rate for the particles is actually quite diverse, which makes it, which is actually something that is part of the game in the process, and it outlines that not all the particles are reacting, the word is are reacting with the CO2 at the same level. And if we look at the gas fractions across the systems, we can see we can confirm what we were actually looking for, that the CO2 is confined somehow to the calciner bed, and steam and H2 are only present in on the other side. You can notice that the water, the steam is actually filling up completely, basically, the loop seal, as you would expect. And the other thing that you can notice is actually that in the inclined pipe here at the bottom, you see that it's actually filled by some hydrogen and some steam, which are not, however, going through to the calciner. This is we assume that this is due to the high diffusivity of H2 compared to the other components. So I mean, so that somehow satisfied the requirements. So we were happy with what we saw. The second point that we wanted to look at was the bubble behavior. Main reason to look into that is because big bubbles entrain the gas, and the gas which is in the bubble obviously tends not to react or not to react well. So you want to keep that situation under control. So ENEA is actually developed their own macro, their own script into TechPlot to classify the bubbles. And you see the isosurfaces here for the calciner and for the reformer. What we actually is interesting, and what was the main aim of this analysis, was to look at the bubbles in the reformer. And you can see here at the bottom there the blue plots where you have diameters over bed height. So, bubble diameters versus bed height, and bubbles velocity versus bed height. And you can see actually that, as you would expect at the beginning, the bubbles tend to be very small. So there are this generation of small bubbles that then, as they move up into the bed, they coalesce and they slow down as well. And in fact, hello. Okay, no, too much. So I go back. Excuse me. Wrong button, wrong button, wrong button. Okay. Right. And if we look at the same thing from in terms of mass fractions, gas mass fraction, you see that you have a large bubble there. This is just an instantaneous shot of picture of what happens in the bubble, you see that the large bubble that you see on the far right, produces unreacted carbon dioxide in the same volume, and has some unreacted methane. And if you look at the H2, you see that green patch means that you probably are losing some opportunity to have a better conversion of H2. So bubbles should be kept under control in this system to have a good efficiency for this system. And it should be said that this analysis actually didn't, for the basic setup that we studied, actually, although we looked into all these details, still proved to be quite efficient. And it's actually being tested right now in the real thing, in Zecomic's pilot plant, because we obtain a very good H2 conversion rate, above around 90%, and at the same time, the CO2 sorption was also quite good. Some other analysis, because obviously, once you got the models, you want to look a bit further into what you're running and into what you have. So after this full system analysis, we looked into a reformer-only model, which was set up using the data we obtained from the complete model. But just to have let's say a smaller model that we could actually use to do some parametric study. And so the idea here was actually to check some reformer operating conditions and to understand the effect on the conversion, on the H2 conversion rate. And the first thing that we looked at was the bed height. And we saw that if you increase the bed height up to twice the nominal one, you obtain, you actually give methane more time to react, because it takes longer to get to the end of the bed, and that obviously helps a lot with the H2 conversion. At the same time, if you play a bit with the fluidization velocity, you can still get some improvements, because again, if you reduce the fluidization velocity up to a certain level, you can actually again reduce the bubble size, so reducing the effect that we saw before, and at the same time, again, you provide some more time for the gas to go through the catalyst particle and sort to react. And in both situations, so there is we obtain that there is some tuning that can be done apart from the nominal setup that was designed at the beginning, and that could just provide the 3, 4, 5% improvement into the conversion rate of hydrogen. So that brings me to the conclusions. We start a dual fluidized bed system with Barracuda, and the system combines some steam, methane reforming, and carbon dioxide capture using bifunctional particles. The model was set up actually to check on a few design aspects that were then implemented into the real pilot plant. So we looked at the system pressure profile, the solids and gas circulation features. We checked the bubble features, bubble behaviors, and then we looked at the impact of operating conditions. Overall, Barracuda proved to be a very efficient tool. And for the investigation of this type of systems. This work is actually been published a few months ago on powder technology, so if you are curious to get some more information or more detail on the results, and you can refer to the paper. It's quite, there's more information, as I said, that I didn't have the time actually to present. And that concludes my presentation. If you have any questions.